Have you ever wondered what empty space really means? Not the artistic kind. I am talking physics empty. Quantum fields fill all of space, but they can sit in different energy states. Most of the time, the state we inhabit looks stable, yet some theories say it might not be the absolute lowest option. It could be a temporary one, like a marble resting in a shallow bowl, while a deeper one waits beneath. The unsettling twist is that the deeper bowl might be reached by quantum tunneling, and when it is, the universe could undergo a phase change so abrupt that causality and the laws of physics as we know them effectively get rewritten. That hypothetical event is vacuum decay. And here's the misconception to kill right away. Vacuum decay is not a bomb going off everywhere. It starts locally, inside a bubble of true vacuum, expanding at near light speed. The question isn't whether it's happening every day. The question is how long such a false vacuum would last, and what determines that lifetime. Because the answer touches not just cosmology, but the deep logic of entropy, probability, and how stable can be only in practice, not by guarantee. To understand vacuum decay, picture a landscape of energies. Instead of hills and valleys drawn for a ball, it's an effective potential for a quantum field, often called a Mexican hat, or more generally, a multi-bow potential. A false vacuum is a local minimal, lower than the surrounding ridge, so small disturbances don't push it out. The true vacuum is the global minimum, the deepest valley. In everyday intuition, the false vacuum should just sit there forever. But quantum mechanics adds a new door, tunneling. Even if a state looks trapped, the wave function doesn't have to respect the classical barrier. It can leak through. Before picture, then, is a universe where our fields, including the Higgs fields in some models, occupy a metastable minimum. Time passes, particles interact, the universe cools and evolves, and nothing obvious happens. Yet beneath that calm surface, the probability of a rare tunneling event is never exactly zero. Now the core mechanism, the bubble, is the key. In vacuum decay, the field doesn't instantly transform everywhere. Instead, quantum mechanics permits a configuration where a spherical region switches from the false to the true vacuum. Outside the bubble, the field remains in the false state. Inside, physics changes according to the new vacuum. The bubble's wall is not a physical surface like a soap bubble. It's a region where the field interpolates between minima. This wall has energy cost, like stretching a membrane. Meanwhile, the true vacuum interior has lower energy, which releases energy. The competition between wall tension and volume energy sets the fate of any would-be bubble. How does such a bubble nucleate? One elegant way to say it is through the Euclidean bounce picture, in a transformed mathematical time coordinate. The most probable tunneling history looks like a bubble that appears, expands to a critical size, then evolves back into real time as it expands outward. There is a critical radius. Smaller bubbles shrink away because wall energy dominates. Larger ones grow because the interior's energy advantage wins. Once a critical bubble forms, it expands rapidly, and the region it reaches experiences the true vacuum. Observers outside the bubble can't receive signals from inside in time because the bubble wall moves near the speed of light, preserving causality in a grim way. You won't see the bubble unless you're already inside the affected region. The entropy burst idea comes in when you consider what happens to available microstates. Different vacua typically correspond to different effective particle masses and interaction strengths, meaning the number of accessible states for matter fields changes. When the vacuum energy drops, the released energy can reheat the region, producing a burst of particles and entropy within the bubble. Not because the universe instantly becomes disordered everywhere, but because the local physics suddenly allows many more ways for energy to distribute. So, how do we compute the lifetime? In metastable quantum systems, decay is exponential at late times. The survival probability looks like xc, where gamma is a decay rate per unit volume. In field theory, gamma is controlled by an action difference, roughly the tunneling exponent. Intuitively, a larger barrier or a smaller energy gap makes tunneling rarer, lengthening the lifetime. Conversely, if the false vacuum is shallow relative to the barrier, the bounce action shrinks and the decay accelerates. In cosmology, expansion also matters. The universe's growth changes the effective spacetime volume where bubbles could appear. Put simply, lifetime is not a single number in a vacuum. It's a competition between how quickly bubbles nucleate and how quickly spacetime volume increases. Now, for the broader implications. Vacuum decay forces a hard question. Is our current state guaranteed or merely waiting? This reframes stability as probability over time, not as certainty. It also links to the measurement-driven story of particle physics. The standard model parameters, especially the Higgs mass and the top quark mass, determine the shape of the Higgs effective potential at high energies. In some ranges, the electroweak vacuum could be metastable, with a lifetime enormously longer than the age of the universe. In others, it could be short on cosmological timescales. That means experiments on terrestrial accelerators indirectly constrain the long-term fate of the vacuum. Vacuum decay also influences early universe thinking. Inflation changes the field's distribution and could push regions of space into different parts of the potential landscape, potentially making false-to-true transitions more likely in some models. Meanwhile, entropy arguments remind us that lower energy is not the same as simple. A true vacuum can drastically alter the spectrum of excitations, which can produce dramatic local reheating and entropy generation, affecting structure formation inside the bubble. The universe's global story depends on rare local events. So what should we take away? Vacuum decay is a specific kind of phase transition. Metastable quantum state tunnels. A bubble of true vacuum forms with a critical radius, and if it exceeds that size, it expands near light speed, converting the local laws that depended on the previous vacuum. The lifetime is encoded in the tunneling rate, which depends on the potential barrier and energy differences, and is often expressed through an exponentially suppressed decay exponent. Entropy enters because the energy released and the new particle content inside the bubble can create a burst of disorder and radiation there, even while the outside remains unchanged. In the end, stable becomes an approximate word. Not wrong, but conditional. The vacuum isn't guaranteed to be the final resting place. It's just the place the universe happened to be sitting when the quantum odds last favored staying put. If you want more physics that challenges what you think nothing means, subscribe for more.